Hello. In today's video, I'm going to talk about problem 1 in this set on series solutions of ODEs. And here's the problem. If Y is this power series, if that's a solution to the ODE you see here, this is actually Chebyshev's equation, 1 minus x squared y double prime minus xy prime plus 4y equals 0. Then its coefficients Cn are related by the equation Cn plus 2 is something times Cn plus Cn plus 1 plus something else times Cn. And you're going to fill in the blanks here with something that involves the n, right? And that holds. I added in my blue. I got some colored pens here, refills of my colored markers. In blue, that's this equation holds for n equals 0, 1, 2, 3, etc., all non-negative integers. And another way of saying this is find the recurrence relation of that ODE. And you might remember last time I talked about to solve an ODE by series solution. Step 1 is find the recurrence relation. And that's what we're doing now. And step 2 is solve the recurrence relation. And that's going to be the next video. All right. So let's just carry on here. So let's rewrite this formula. Y is sum from n equals 0 to infinity Cn x to the n. That's C0 plus C1x plus C2 x squared plus C3 x cubed plus dot, dot, dot. All right, so that means that y prime is going to be sum n equals 1 to infinity. I'll talk about that a little bit more in a second, of n times Cn times x to the n minus 1. Right, so to differentiate x to the n, that's the thing we love to do. The derivative of that is n times x to n minus 1. And what do we get? The derivative of this constant is 0. So I start out with C1x plus 2C2. Sorry, I start out with C1 plus 2C2x plus 3C3x squared plus dot, dot, dot. Right? You see, that's why I start with n equals 1. When n equals 1, I get this term here. And n equals 1, I get 1 times C sub 1 times x to the 0. 1 times C1 times 1, in other words, just C1. And then here's y double prime is going to be sum from n equals 2 to infinity, n times n minus 1 times Cn times x to the n minus 2. And then this, when I differentiate this line, that term goes away. I'm just left with 2C2 plus 6C3x plus dot, dot, dot. And you see, that's what I get when I put in n equals 2 in this formula. 2 times 1 times C2 times x to the 0. And then when I put in n equals 1, I get that term, right? Okay. So let's just plug these into the differential equation. Now I'm going to write this differential equation. Well, I think I'll just write it up here to get it in, so I have it. Okay, and then I'm going to rewrite it before I plug these in. Breaking this into two terms, because I'm going to handle the y double prime and the y double prime and the x squared y double prime separately. All right, so you get y double prime minus x squared y double prime minus xy prime plus 4y equals 0. Okay, so let's plug this guy in here. Here we go. This one is sum from n equals 2 to infinity, n times n minus 1 times cn x to the n minus 2. And now, when I take x squared, I guess I'll just write it out. X squared times this same sum. And then I get minus x times this sum. That's here. And then I have plus 4 times n is 0 to infinity, cn x to the n, and that's got to be 0. All right, so at this point I can erase all of this stuff. And all right. So one thing I want to do here is do a few things. One is I want to be able to combine these guys all. So I want to have x to some common power. And let me just start with these two terms. Notice that x squared times x to the n minus 2 is x to the n. So that's pretty cool. And here I have x times x to the n minus 1 is x to the n. So in fact, these three terms are all automatically involving x to the n. And what I want to do, I want to call this x to the n, but it's not. So let's call it x to some single variable. I'll call that m. So I'm going to let m be n minus 2. And I did this on the previous video. Okay, so that means that n is m plus 2. And let's also think about the limits. N equals 2, the first term in the sum, n equals 2. If n equals 2, then m is 0. In fact, if m is 0, then n is 2. So that goes back and forth. So now I can rewrite this as sum from m equals 0 to infinity, but n is now m plus 2. Times m plus 2 minus 1 is just m plus 1, times c sub m plus 2, right? Because n is m plus 2. And then here's the payoff. This is x to the m. And then I have minus sum from n is 2 to infinity, n times n minus 1 times cn x to the n, minus sum from n equals 1 to infinity, n times cn times x to the n, plus 4 times sum n equals 0 to infinity, cn x to the n equals 0. So at this point, you see, we're in pretty good shape. We got an x to the n, x to the n, x to the n here. Although the bottom, the first value of m in the sum, the bottom value of n, is different. So let's think about that in a while. But then this is x to the m instead of x to the n. Well, that's easy to handle. M is just a dummy variable. I'm just going to replace m by n. So here I'm going to replace m by n. And what am I going to do over here? I notice that if I start with n equals 0 to infinity, everything gives me the exactly the same sum, because when n equals 0, because of that factor, I get 0 times -1 times c sub 0 times x to the 0. And then when n equals 1, I get 1 times 0 times c1 times x to the 1. Both of those are 0. So here, starting with n equals 0 gives the same sum. And that doesn't always happen. And you notice that the first video is a lot like problem 2 in this webwork set. You can't do this trick. So this is a trick that often works, but not always. And here, the same thing happens. When n equals 0, if I start the sum from n equals 0 to infinity, I get the same sum, right? So let's just rewrite it again. I get sum from n equals 0, because now it's n instead of m, the dummy variable, times n plus 2 times n plus 1 c sub n plus 2 x to the n minus sum from n equals 0 to infinity n times n minus 1 times cn times x to the n minus sum from n equals 0 to infinity n times cn times x to the n plus 4 times sum from n equals 0 to infinity cn x to the n equals 0. Whew, okay, so this was really my goal. Now I've got 4 different sums that all have exactly the same power of x inside. They're all x to the n, and they all start with n equals 0, summing up to n equals infinity. So I can take these 4 sums and write them as a single sum. And that's what everything I've been doing up to this point was leading me to. So I get that differential equation is the same thing as a sum from n equals 0 to infinity of, I'm going to make a big bracket. So that's the big picture is this. It's the sum from n equals 0 to infinity of something with no x's, but it has n's in it, it has cn's in it, times x to the n is 0, right? And what's that thing inside there? First, this term, I've got n plus 1 times n plus 2 times cn plus 2, all times x to the n, but that's factored out. Then I have minus n times n minus 1 times cn. Okay, there. All times x to the n, good. And then I have minus n times cn. That takes care of that term. Then I have a plus 4. Okay, good. Times cn. Okay, good. Plus 4 times cn. So in order for this to be this function to be 0, remember that 0 is really 0 plus 0 times x plus 0 times x squared plus dot dot dot, right? So I need to have this thing equal 0 for n is 0, for n is 1, for n is 2, etc. So let's write that a little and simplify it a bit. We get n plus 1 times n plus 2 times cn plus 2 equals. Let's notice that all of these terms have a cn in them. So let's factor out the cn, and I'm also bringing it to the other side. This is going to be a plus n times n minus 1, a plus n, and then a minus 4, all times cn, right? So this thing inside the square bracket equals 0. set it equal to 0, then I bring these three terms to the right-hand side, is what I've done here, and put in the negative. And you notice that this is going to simplify a bit. This is n squared minus n plus n minus 4 times cn. Right? So in other words, what do we got here? We got n plus 1 times n plus 2 times cn plus 2 is equal to n squared minus 4 times cn. Right? Oh, but n squared minus 4 is a difference of squares. This is equal to n plus 2 times n minus 2 times cn. Okay? And I can cancel those two terms, and what do I get? I get n plus 1 times cn plus 2 is equal to n minus 2 times cn. All right? So I'm almost done. So I get the recurrence relation of this ODE is, and in the recurrence relation, we typically solve for the C with the highest coefficient. It's going to be, drum roll please, it's going to be Cn plus 2 is equal to n minus 2 over n plus 1 times Cn. And that's true, got to be true for n is 0, 1, 2, 3, 4, dot, dot, dot. All right. So to answer the webwork problem, if this were your problem, it would be Cn plus 2 is a blank times Cn plus 1 plus another blank times Cn. You'd fill in a 0 here, and you'd fill in n minus 2 over n plus 1 in here. Okay? All right. So let me just talk a little bit about it. I'm going to solve this next time. But a little bit about it to say note. C0 and C1 are arbitrary. This recurrence relation says nothing about what C0 and C1 is. The first equation is, when n equals 0, is C2 is something, and then C3 is something, right? So the recurrence relation gives C2, 3, 4 all in terms of C0 and C1. Okay, and that's what we call solving the recurrence relation. Solving the recurrence relation, C0 and C1 are arbitrary, and then we find out what all the other C's are in terms of C0 and C1. Or alternatively, you might have an initial value problem and say, I want to solve this in differential equation with, say, y of 0 is 7 and y prime of 0 is 3. What would I do? This means that C0 is 7 and C1 is 3, right? Remember, those first two coefficients in the Taylor series tell you the value of the function and the derivative. So that's the other thing. I might start with C0 is 7 and C1 is 3, and then the recurrence relation tells me what C2, C3, C4, C5, etc. all are. Okay, well, as I say, next time we'll go through and see and solve this kind of in this first thing. We'll keep C0 and C1 arbitrary next time and see what the general solution to this ODE is. All right, bye.